Right, this is the third and final of the three chips we need to get to know how to use. So we've dealt with the timer one last, we dealt with the PIA before that, and now we're going to deal with the ACIA, the serial chip, the 6850. So let's get on with it and see how that works. Right, so we've still got our timer chip because we're still going to use the same timing code that we developed in the previous example. We've still got the PIA because we're still going to blink our little LED. We've still got our little LED in there. And what we've added is the ACIA. And this is the one that I'm most familiar with because on my own board, I use the same chip. It's down here. This is the ACIA over here. So this was not a challenge. I mean, the tricky bit here was like I said in the introductory video, is I got the cable wrong. So once I figured out the cabling, magic started to happen. But it was really painful to figure that out. Anyway, let's get on with it and see what's different about this one. So it's got some helper functions that I borrowed from the Hopper runtime, like a write character, which takes what's in the A register and writes it to the serial port. I've got a hex out, which takes what's in the A register, breaks it into most significant and least significant nibbles, and calls write char, makes the hex output. Nice for outputting hex numbers. We still don't. I've got a non-maskable interrupt handler right now. I haven't had that in before, even though we're not firing non-maskable interrupt ever. Our IRQ is exactly the same still, and that's because I didn't bother doing an interrupt handler for the ACIA in this example. It's nice to do it on the RX. I think it's the RX. I'm dyslexic. I get things switched around. So yeah, RX interrupt. So I didn't enable RX interrupt, so it's not arriving, and that's because I'm not bothering to make this. I'm only bothering to output content via the serial port, not bothering to read it in this example. So this is how we set up the ACIA. We reset it, and then we set up stop bits and speed and all that. This is an old comment. Yes, that should probably be 4 megahertz. But oh no, it was correct. Yes, important. Good point. It's not the CPU crystal. It's the CAN oscillator for the ACI, which is 4.9152. Right. So this sets up the baud rate and stop bits, parity bits. How many bits? 8-bit, no parity, 1 stop bit. The default that is in the Hello World example from Digicool Things uses 2 stop bits. Slightly different to this one. My usual protocol with my terminal in Hopper uses these settings. Datasheet's pretty good for figuring out the rest, or just ask on the forum. And then I output a new line to the serial, and I output a colon just to show that we've arrived. And then just for fun, I put an open brace and a closed brace before and after we initialize the timer. Same thing with the blinking again. Setting the data. Oh, that's a typo. That needs to be a 1. Data direction for output. Select port A. It's selecting port A on every loop over here, so it doesn't need that. Don't know why I did it differently, but it's been a while. Anyway, select port A, write 1 to it, blink it, write a 0 to it, it's off. And then I've got this thing called seconds, which is another 0-page variable. And in theory, every time we come around this loop should be a second, because it's 500 milliseconds there and 500 milliseconds there, which means our output of seconds here, hex output of a second. So I use this to calibrate with a stopwatch, just to time where it says 20 seconds and look on my watch and see if it actually was 20 seconds. And it is spot on, of course. And then this here is most significant bit first, byte first, putting out the tick. So the first thing we should see come out of the tick is whatever we configured it to. And we're running at 4 megahertz. So the first thing we should see coming out would be hex for 4,000. And the second thing it should come out is hex for 8,000, etc. And I've put in the comment here, if you're running at 4 megahertz, it's, 4,000 clock cycles per 1 millisecond period. If your clock's running at 1 megahertz, then divide by 1,000. It's 1,000 milliseconds, 1,000 clock cycles per millisecond. All right, let's build this. And I'll do the same thing I did last time. 65 DASM-OG-C, and this was called ACIA Blink. All this source is in the repo on GitHub under the MECB 6502 folder. And let's go have a look at this code. Debug blink.listing. So there you go. That's sort of conventional look for what the assembler looks like. To show you what it looks different, if I don't put in those options, then it's in the Hopper 6502 assembly format, which has got the comments original before optimization, so they don't always line up. So and it's got comments like C, and it's got the hex like C, etc. So there's two different assembly formats that the disassembler can output, depending on which preference is. All right, let's program our EEPROM again. So let's go get it. ACIA Blink, 32K ROM, which means it starts in the address space at 32K, which is 8000 hex. And now we have all three vectors because I added the empty NMI vector. We should be able to see that in here somewhere. Should just be an RTI. Yeah, there it is. So the NMI vector is, all it is just a return. That's the default if you add that to your program without actually putting any code in this program. All right, I'm going to pause, put in the chip, and then turn it on again so that I can get my microphone and my camera not be messed up by me trying to mess with the chip. Okay, we're back, and we've got the chip plugged in. So if I turn it on, I should start to see little blinky light going again. There we go. But this example is slightly different in that let's check the baud rate of our terminal connection. I'm at very slow baud rate, 9.6. And then if I launch the terminal app, there we go. We've got output coming. Now, if I reset this, you're going to see that initial, let's just hit the reset button, hold it down, release it. So yeah, the little brackets were where we were initializing the timer, and then these are the seconds counting by. So you can rewind the video, run it again, and see if these count or not. And like I say, the first would be 4,000, 8,000 decimal. So that's the hex. All right, very good. So that's about as much sample code as we need to get going. I mean, I wish I had the sample code before I tried to do this. And why did I do all this? The main point of all this was to write the drivers for Hopper. But I figured since I've been through all this trouble to get to write these drivers, I might as well share the effort. So there'll be one more video at the end of this, which shows you that Hopper we'll do a blink in Hopper running on this platform now, because we've got the whole of Hopper working. And I'll spend a little time explaining how you configure Hopper to build for a machine other than my own machine. Because we've got it running on a few machines now. Yeah, there's several different 6502 machines now running Hopper. Anyhow, thanks for watching, and stick around for the Hopper one. It's coming next.